Hey everybody, welcome back to number theory. I have a few more things to say about prime numbers. Most of them are not deeply theoretical, just informative. And the first thing I want to talk about are twin primes. Twin primes come in pairs, p sub n and p sub n minus 1. And as the notation indicates, if p sub n is the first number of the twin prime pair, and p sub n plus 1 is the second number of the twin prime pair, it also is the case that they are consecutive primes. So in other words, if p sub n is the nth prime, and p sub n plus 1 is the n plus first prime, and the two of these constitute a twin prime pair, then they're exactly 2 units apart. Our definition says that p sub n and p sub n plus 1 are twin primes, or constitute a twin prime pair, exactly when the second number of the pair is 2 greater than the first. Now, can we think of some examples of twin prime pairs? So let's see, 3 and 5, 5 and 7, 7 and 9, no, that's not going to work. But what about 11 and 13, 13 and 15, no, but 17 and 19, they'll work. Oh, let's see. 19 and 21, no. 21 and 23, no. 23 and 25, no. 27, 29, no. 29 and 31, they're both primes, aren't they? Okay, so there's another twin prime. See, 33 and 35 are not prime. 37 is prime, but 39 is not. What about 41 and 43? I think they're both prime. So these are some examples of twin prime pairs. Now we might notice something. All of the twin primes are odd. In order to have a twin prime pair that was even, both numbers would have to be even and they both have to be prime. And the only prime number that's even is 2. So there are no such things as twin prime pairs. And 2 and 3 are actually closer than twin primes. 2 and 3 are consecutive numbers. They're the only prime numbers that work that way. The only 2 prime numbers that differ by 1 unit are 2 and 3. And if you think about it, it makes sense. If 2 numbers differ by 1, if 2 natural numbers differ by 1, then one of them is going to be even and one of them is going to be odd. Well, in order to have a pair of prime numbers that are 1 unit apart, one of those numbers has to be even. One of those prime numbers has to be even, which means that 2 has to be one of the numbers in the pair. Okay, well, what about 1 and 2? They're 1 unit apart. They are, but 1 is neither prime nor composite. A prime number has to be of size 2 or greater, as does a composite number. So if we have 2 primes 1 unit apart, one of those, and one of them is even, well, that number has to be 2. 1 and 2 can't be the pair because 1 isn't prime. So the only possibility is 2 and 3. There's only one pair of primes that are 1 unit apart, 1 and 3. There seem to be a whole bunch of pairs of prime numbers that are exactly 2 units apart. And so we have a name for these. We call them twin prime pairs or just twin primes. The twin prime conjecture. I'm not going to say this is a theorem. I'm going to say that it's a conjecture. The twin prime conjecture says that there are infinitely many twin prime pairs. It's a conjecture that we don't know whether this is actually in fact true or not. Number theorists seem to think that it is true, although so far nobody's been able to prove it. This conjecture goes back probably about 2,000 years. And while 2,000 years ago someone was clever enough to prove that there are infinitely many prime numbers, to this day nobody has been able to prove that there are infinitely many twin prime pairs. And nobody's been able to prove that there aren't infinitely many twin prime pairs. This is probably the most famous problem in number theory. It's a famous problem in mathematics. Back in the early 1980s, when I was working on my master's degree, I saw a letter from the American Mathematical Society posted on the bulletin board of the department. And it announced that it was offering a $10,000 reward for anyone who could prove one way or another whether this conjecture was true. And this person would collect the $10,000 if after 1 year of submitting their proof, the proof stood without being refuted by other mathematicians. So I told my advisor that I was going to work on that problem, and he said, well, that's a nice problem to work on. It's a very famous problem, and I don't want to discourage you. I'm glad that you're interested in this. But let me tell you something. A lot of the most famous mathematicians, even in the 20th century, have devoted their entire careers to working on this problem, and they have not been able to solve it. And they are number theorists. They have not been able to prove this or refute this. I'm not trying to dampen your enthusiasm, but I'd like you to have a realistic idea of what your chances for success are. And let's see, like I said, that was in the early 1980s, so almost 40 years ago. This is still unproven one way or another, but it is one of the hottest topics in math. Now, let's see what we do know about twin primes. Just a little information about twin primes to whet your appetite. So let's see. $150 some odd thousand twin prime pairs, and maybe I should be very, very specific about this. 150,000 plus twin prime pairs, less than 30 million. Okay. Oh, I see. I guess this was correct all along. 150,000 pairs of twin primes less than 30 million. Okay. No. Let's see, 10 to the 12th, let's see, 10 to the 6th is millions, 10 to the 9th is billions, so this is a trillion. So between 1 trillion and 1 trillion plus 10,000, there are only 20 twin prime pairs. So there are 10,000 natural numbers between these two, and only 20 twin prime pairs. So it appears, and I will say appears, so as the numbers get larger and larger, it appears that twin prime pairs get more and more scarce. That is a fact. No, no, no. Now, I guess this looks like a big number or a big pair of numbers. The twin prime pair consists of this number plus or minus 1. Now, how big is that? Let's see. These two numbers are 388,342 digits in length, okay? So in other words, take 10 and raise it to this power, and that's essentially how big the numbers are. Let me give you an idea of how big this is. It's my understanding that this number is much, 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 much bigger than the number of atoms in the known universe. So that's how big these two twin primes are. The largest twin primes discovered to date. A little bit more information on primes and twin primes. One of these things I think will genuinely tickle you. So the difference between consecutive primes can be arbitrarily small. Twin primes, they're 2 units apart. And there may be infinitely many of these pairs. We don't know. So consecutive primes can be fairly close together, twin primes. And there may be infinitely many of these twin primes. distance between consecutive primes can be arbitrarily large. In other words, pick any number, any natural number, as large as you want, and we can find consecutive prime numbers that are at least that far apart. Think of a large number, a large natural number, a million, billion, trillion, quadrillion, blah, blah. We can find consecutive numbers that are that far apart, consecutive prime numbers that are that far apart. So there are consecutive prime numbers with a million, billion, trillion, quadrillion composite numbers in between them and no primes. And the proof for this is rather clever. And there's a little bit of humor here too, I think, at least in my mind, mathematical humor. Let's see, how would we prove that for any natural number n, no matter how big it is, there are two consecutive primes that are at least n units apart? Let's say that n is a million, billion, trillion, quadrillion, or whatever. How could we show that there are two consecutive primes that are at least this far apart? The way to do it is to show that there are this many consecutive composite numbers. If there are this many consecutive composite numbers, then the greatest prime less than those composite numbers and the smallest prime larger than those composite numbers are consecutive primes that are at least this far apart. So the way to show that there are two consecutive prime numbers at least this far apart is to exhibit this many consecutive composite numbers. And this is how we do it. Oops. Let's see. Here's the first. Here's the second. Here's the third. And notice this thing is 1 less than that thing. If this is first, this is 2. If this is second, this is 3. If this is third, this is 4. Or looking at it the other way, if this is 2, this is first. If this is 3, this is second. If this is 4, this is third. So this is n. So this is the n minus first. This is n plus 1. And 1 less than n plus 1 is n. So nth. All of these numbers are composite. They're n consecutive composite numbers. This one's 1 bigger than that one. This one is 1 bigger than that one, and so on. Now, the only thing I really haven't justified completely yet is how it is that I know that each of these things is composite. So let me just do some scratch work here. If you don't see it yet, you'll see it in just a minute. And this is really, really clever. I think you'll like it. Now, how is it that I know that all of these numbers are composite? How do I know? Let me see. Well, what is n minus 1 factorial? Isn't n minus 1 the factorial? N minus 1 times n n plus 1 times n minus 1 times n minus 2, times 3 times 2 times 1. N plus 1 factorial is n plus 1 times every natural number less than itself. In particular, 2 is a factor of n plus 1 factorial, and 2 is a factor of this term. 2 divides both of these terms, so 2 divides the sum. And I will denote that in just a second. I'm going to get myself a red marker that actually writes. So 2 is a factor of this thing. Now let's look at this number. N minus 1 factorial is the product of n plus 1 factorial is the product of n plus 1 and every natural number less than itself. So 3 is a factor of n plus 1 factorial, and 3 is a factor of this term, so 3 is a factor of both. 3 divides the sum. And Yeah, you guessed it. 4 is a factor of this one. And n is a factor of this one. And n plus 1 is a factor of this one. So here we have n consecutive composite numbers. Now there are infinitely many primes, so there are definitely prime numbers larger than this. And there are prime numbers smaller than this. But there are no prime numbers in between. So the greatest prime number less than this and the smallest prime number greater than this are consecutive prime numbers, and they're at least n units apart. So consecutive prime numbers can be arbitrarily far apart. Oh, some other things. Goldbach was a famous number theorist from years and years and years ago, and this was one of his speculations. Let's see. Every even number greater than or equal to 4. So 4, yep, it's the sum of 2 primes. 6, yep, it's the sum of 2 primes. 8, yep, it's the sum of 2 primes. 10, it's the sum of 2 primes. 12, let's see, sum of 2 primes, etc. So every even number greater than or equal to 4 is the sum of 2 primes. That's his conjecture. This is another famous conjecture from number theory. We do not know whether it is true or not. Now, this is a corollary, an immediate corollary of Goldbach's conjecture. Okay. Before I do that, let me restate Goldbach's conjecture. Four gets left out of this, but let's look. 6 is 3 plus 3. 8 is 3 plus 5. 10 is 3 plus 7, or 5 plus 5. 12 is 5 plus 7, and so forth. So this is a slightly stronger statement. It's not just saying that every even number greater than 4 is the sum of two primes. It's saying that every even number greater than 4 is the sum of two odd primes. So that would let 4 out, but it doesn't let the others out. Now let's do a corollary. So n greater than 7 is odd. And so n minus 3 is even. And n minus 3 is also greater than 4. because n is greater than 7 by hypothesis. So by Goldbach's stronger conjecture, n minus 3 is equal to P1 plus P2, where P1 and P2 are odd primes. This implies that n equals n minus 3 plus 3, which is equal to P1 plus P2 plus 3 is the sum of 3 odd primes. So assuming that Goldbach's stronger conjecture is true, then the corollary, every odd number greater than 7 is the sum of 3 odd primes, is true. Those are not terribly challenging exercises. What they are just exercises to familiarize us with twin primes and things like that. So review the notes, please, and crank these out. And in a day or two, I'll have another lecture. This one essentially on modular arithmetic. Some of you who have had abstract algebra are familiar with this. But the topic is called congruences. And when I say congruences, we mean congruences modulo n. So we'll talk a bit about the theory of congruences and get into that a little bit before the end of the term. It's definitely something we should see.